The goal of this video, as I mentioned in class today, is to help everyone become more comfortable with real-world piecewise functions. And so let's first go over number one. Now, this is a redo of notes that we did, and then I'll also apply this same concept to the homework. So our first question says, according to the U.S. Census Bureau, the population of Tucson, Arizona was 45,000 in 1950. From 1950 to 1970, it grew at an average rate of 10.9 thousand per year. After 1970, the population of Tucson grew at an average rate of 7.5 thousand people per year. Question A asks us, find a piecewise linear function, P of t, that gives the population P, so there's one of my variables, as a function of the year t. So we will start off by making a note of our variables. Our variables will be t, where t is the number of years since 1950, because 1950 is our 0 year. And P of t will be our population in thousands. And for space, I'm actually going to set that right here. T is my number of years since 1950, and P of t is my population in thousands. So when we look for our first piece, we're going to say P of t equals, we reread, in 1950, I have my initial value of 45,000. From 1950 to 1970, I have an increase at a rate of 10.9 thousand people per year. So that's where 10.9 T plus the initial value in 1950, which was 45. Because my population, my output is defined in thousands, I can just write 45. I don't need to write 45, 000. And that is between 1950 and 1970. Because 1950 is my 0 year, this will be from T is 0 to 20. So that piece exists with the restriction of T between 0 and 20. Now, all of us were 100% comfortable right up to this point. The new idea that I'd like to talk with you about directly connects to point-slope form. So remember, point-slope form. Y minus y1 equals m times x minus x1. So this population is connected from year to year. So where 1970 leaves off, I need to know what that value is, because the next year is 1971, will be involved in our next piece, but there is an existing population. So what we are going to do is calculate P of 20 off to the side. P of 20 equals 10.9 times 20 plus 45. So let's take our calculator. We're going to do 10.9 times 20 plus 45, and we get 263. So from that, I get the ordered pair 20, comma, 263. There's my ordered pair. So that means in 1970, the population was 263,000. That will be the starting point of, or be involved in the starting point of my next segment. My next piece, it says, after 1970, the population of Tucson grew at an average rate of 7.5 thousand. This is going to be the slope, m, that we use in point-slope form. So we're going to use this this slope and this point in point-slope form. So this will become y minus 263 equals 7.5 times x minus 20. When we solve this, we will actually have the entire expression that we need for our next piece. So that becomes y minus 263 equals 7.5x. We do 7.5 times 20 and get 150. So this is minus 150. Add 263 to both sides. Y equals 7.5x plus 113. So my next piece is 7.5x plus 113, and that is for all years after 1970, so for all years where t is greater than 20, and I'm done. So again, to highlight our new, more direct strategy, I have my initial piece, and I know that's from year 0 to year 20. Well, population doesn't just start all over again at 0. There is going to be an initial value. To figure that out, we are going to plug in, we're going to substitute 20. We're going to calculate P of 20. When I calculate P of 20, my output is 263. That becomes the ordered pair 20, 63. This ordered pair and the slope, the rate of change of the next piece gets substituted into point slope form. I solve, and that will get me the expression I need for the last piece. Let's talk about our follow-up questions. B says, use your model to predict the population of Tucson in 2010. 2010 is a year. I need to figure out how many years after 1950 is 2010. So we can subtract. We can do 2010 minus 1950. That equals 60. P of 60. Well, we need to ask ourselves, where does 60 fall into the restrictions? Is it between 0 and 20? No. Is 60 greater than 20? Yes. So I know I'll be using the second piece. So that will be 7.5 times 60 plus 113. That gets us 563,000 people. C asks, according to your model, in what year did the population of Tucson reach 100,000? 100,000 will be a value for our output, my actual population amount. And in class, we had a great conversation. 100,000 we're going to look at as 100 because population is defined in thousands, so we'll see that as 100. In class, someone picked up that on our second piece here, the initial value is 113. 100 is less than 113, which means I must be in this first piece. That is how we know to set 100 equal to 10.9t plus 45. We'll solve this. We'll subtract 45 from both sides. We get 55 equals 10.9t. Divide by 10.9. Divide by 10.9. T equals 5.05 years later. To figure out what year that is, we have to again remember that T is the number of years since 1950. So this will be in the year 1955. 1950 plus 5 is 1955. Now we're going to apply our strategy again to number 2. Let's talk about number 2. According to the U.S. Census Bureau, the population of Charlotte, North Carolina was 18,000 in 1900. From 1900 to 1950, it grew at an average rate of 2.32 thousand people per year. After 1950, the population of Charlotte grew at an average rate of 6.26 thousand people per year. So we're going to break this down. We see that 1900 will be our 0 year. So let's first define variables. So T equals number of years since 1900. P of T will again be population in thousands. With that in mind, let's reread and find our first piece of information. I know that in 1900, the population was 18,000. That is an ordered pair. That's a fact that we're about to use. Our first restriction will be from 1900 to 1950. Again, 1900 is our 0 year, so 1900 really represents 0, making 1950 50, because 1950 is 50 years after 1900. So we look, between 1900 and 1950, the population grew at a rate of 2.32 thousand people per year, where in 1900, that initial year of 1900, the population was 18,000. So that's where I know plus 18 comes from, because it tells me in 1900 the population was 18,000. That expression is restricted for the first 50 years. So T is greater than or equal to 0 and less than or equal to 50. We've established our first piece. So again, population doesn't just reset. We don't start back at 0. I need to figure out how this piece connects to the next one. To figure out that connection, we're going to take 50 and substitute it into the first piece. We're going to calculate P of 50, which would be 2.32 times 50 plus 18. So 2.32 times 50 plus 18. I get 134. So ask yourself, what ordered pair comes from this calculation? When x is 50, the population is 134. I now have an ordered pair, x1, y1, which will be on my next expression. I need to go back and reread and find the rate, my m value for this next piece. And I read, says, after 1950, the population of Charlotte grew at an average rate of 6.26 thousand people per year. So there is my m. We're going to take this ordered pair and this slope and substitute into our point slope form. So that will become y minus 134 equals 6.26 times x minus 50. When we solve this for y, we will have the expression that goes right here. So let's solve. It's going to be y minus 134 equals 6.26x. We're going to do 6.26 times 50, which is 313. And we'll solve by adding 134 to both sides. We get y equals 6.26x. If I do 134 minus 313, or negative 313 plus 134, same thing, we get minus 179. This expression is my next piece. So I have 6.26t minus 179. That is for any year after 1950, so for t greater than 50. And we're done. So again, let's talk big picture. The strategy. We're all good getting this first piece. It's figuring out what comes next. To figure out what comes next, we are going to take the largest t value, in this case 50, of this piece. We substitute it into the expression, and when we did that, we got 134. That becomes the ordered pair 50, comma, 134. We take that ordered pair and the rate of change, the slope for the next piece, we substitute this m value and this x1, y1 value into point slope form and solve. What we get as our answer will be the exact expression. I literally took my answer here, 6.26x minus 179, and I wrote it right here. This expression is for all years after 1950. So 1950 is represented by 50. So all years after 1950 would be t greater than 50. Let's answer our follow-up questions. Based on your model, what was the population of Charlotte in 1980? So we need to figure out 1980 is how many years after 1900. We may see it naturally. If not, that's okay. We can subtract 1980 minus 1900 equals 80. We ask ourselves, is 80 between 0 and 50? No. Is 80 greater than 50? Yes. So I know I will be using my second piece. So P of 80 equals 6.26 times 80 minus 179. When we use our calculator to do that math, we get 321.8 thousand. C asks, use your model to determine in which year the population of Charlotte grew to 500,000. Again, we will interpret 500,000 just as 500. To figure out which piece we use, I see that I have an initial value of 179,000. But it says negative, so I really don't think I can use this the way that we did before. But we do have something we can use over here. You know, in year 50, or in this case, means 1950, the population was 134,000. Well, 500 is way bigger than 134. So that means right away I know I will be using my second piece. So we're going to set 500 equal to 6.26t minus 179, and we'll solve. So we're going to add 179 to both sides. So I have 679 equals 6.26t. We'll divide by 6.26. That gets us t equals approximately, so let's make a little wavy line, 108. 108 years after 1900 becomes the year 2008. Great. Let's talk about number 3. According to the U.S. Census Bureau, the population of San Francisco was 775,000 in 1950. From 1950 to 1980, it declined at an average rate of 3.2 thousand people per year. After 1980, the population of San Francisco grew at an average rate of 4.9 thousand people per year. So I know 1950 will be my 0 year. Let's let t equal number of years since 1950. P of t will be defined as population in thousands. And let's get to it. So P of T equals, let's read for information. I know in my 0 year, I have an initial value of 775. My first chunk of time is from my 0 year to 1980. It says declined at an average rate of 3.2 thousand. If it's declining, it's a negative rate. So negative 3.2 T plus that initial value of 775. This will become 0 to 30 because 1980 is 30 years after 1950. So T greater than or equal to 0, less than or equal to 30. I have my first piece. Fantastic. How do I make the connection to the next expression? We are going to take 30 and substitute 30 into this expression. So that will be P of 30 equals negative 3.2 times 30 plus 775. So in our calculators, negative 3.2 times 30 plus 775 equals 679. That gets me the ordered pair 30, 679. We're going to use this ordered pair and the rate of the next expression to actually do our math. So if we read, we already used that, after 1980. So we're set up to 1980. We've done this. After 1980, the population grew at an average rate of 4.9 thousand. There is our M. So we're going to use Y minus 679 equals 4.9 times X minus 30 to find our next expression. So let's solve that. Y minus 679 equals 4.9x. That'll be minus 147. I add 679 to both sides. We get y equals 4.9x. 679. Keep typing it into the calculator wrong. That's not helping. 679 minus 147, or negative 147 plus 679 gets you plus 532. This is the expression I need for my next piece. So I literally take this, 4.9x plus 532, and I write it right here. 4.9x plus 532, and that is for all years after 1980. But I'm not going to write 1980. We're going to write t greater than 30 because 30 is the t value that correlates to 1980, and we're done. Make this a little smaller. Based on your model, what was the population of San Francisco in 1975? We do 1975 minus 1950. We get 25. Let's ask ourselves, is 25 between 0 and 30? Yes, it is. So we'll use our first piece. We're going to use this piece. Because 25 falls between 0 and 30, we will use our first expression. So P of 25 equals negative 3.2 times 25 plus 775 plus 775. And so let's see, I got 695,000 people. Use your model to determine the year in which the population of San Francisco returned to its 1950 level. So for it to ask us that question means we must know something about 1950, and in fact, we do. If we go back and read for information, we know in 1950, the population was 775,000. To figure this out, we also, again, just need to reason. Now, from years 0 to 30, the population was declining. So do not be tempted when you see 775 and 775. No, 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 no. We're saying that initially, in 1950, this was the initial population. And from 1950 to 1980, that population was getting smaller and smaller and smaller and smaller, which is why in 1980, 1981, if you check this out, our initial population is 532,000. It's here, it's starting in this year that our population is growing. I have a positive rate of change. So I know based on that, I will be using this expression. Another way to reason, as long as you mentally cross this off in your brain, is that 775 is greater than 532, so I will definitely be in this piece. However it works for you to think about it, that's what you need to do. Whatever your thought process, as long as it gets you to deciding to use the second piece, that works. So 775 equals 4.9x plus 532. We'll subtract 532 from both sides. So 775 minus 532. I get 243 equals 4.9x. We'll divide both sides by 4.9. I get x, all of these x's, I just realized this should not be x. This should be t. So 4.9t, 4.9t. So now I have t equals approximately 49.6. So 49.6 years after 1950. When I add that, you get 1999. The homework that was associated with these notes started with this question. And this question I already filled out because most of us did a really nice job and got this right. I didn't want to necessarily focus on it in the video. Here we have 4 fixed costs. Children 5 years old and under. A question came up after school, where did this 0 come from? And it was a good question. We have to think about time. I'm not going to put negative infinity here because we can't have negative time. The smallest possible age, I'm sorry, we're not talking time, age. We can't have negative age. The smallest possible age is 0. So this becomes 0 to 5, you're free. The cost is 0. And that's reflected here. From age 0 to 5, so 5 is halfway between 4 and 6, the cost is 0. Between 5 and 12 years old, the cost is 10. I have my next step. Between 12 and 18, we jump to $25 a person. And now older than 35, the cost is 18. Here we will have array because this amusement park is not saying if you're between 35 and 101 or 35 and 86. It's just saying 35 and older, that's how much you're paying. So that is the reason why here we do have array that will keep going forever and ever. Let's bring back our note strategies that we just talked about and work on 2 and 3. Income tax. So I have income tax is 5% on the first $50,000 of income or less. and 8% on any income in excess of $50,000. Let the tax T of X be a function of income X. So this is nice. It helps define our variables already. So just so I have plenty of space here, I'm going to define them up here. X is income. And my output, T of X, is tax. Both measured in money, so we'll have to be careful we just keep track of what's what. So I'm told X is my income, tax is T of X. So we have T of X equals, let's work on building the first piece. It says income tax is 5%, so 0.05X on the first 50,000 of income or less. So if my income is between 0 and 50,000, this is my rate. Again, we cannot have negative money, so 0 will be a real-world lower limit on our X values, on our income. Notice, unlike the population examples, I do not have an initial value. I'm just straight up told 5% on money, on income between 0 and 50,000. Done. My next piece tells me 8% on any income in excess or more than this much. So I have M. I need a point. To find that point, we are going to take 50,000 and substitute into this function here, this piece. So it's going to be T of 50,000 equals 0.05 times 50,000. So let's do that. 0.05 times 50,000. And I get from that 2,500. So my ordered pair will be 50,000, comma, 2,500. For space, we're just going to slide this up a little bit. So I now have my ordered pair. And my M. Here's X1, Y1, and here's M. So let's go for it. Y minus 2,500 equals 0.08 times X minus 50,000. That becomes Y minus 2,500 equals 0.08X. I'll do 0.08 times 50,000. I get 4,000, so minus 4,000. Add my 2,500 to both sides. My final expression will be Y equals 0.08X plus 6,500. So this expression is what goes right here. 0.08X plus 6,500, and that is for any income in excess or greater than 50,000. And I am done. Number 3 says, for a cellular phone billing plan, $50 per month buys 400 minutes or less. Additional time costs 30 cents per minute. Let the monthly cost C of X be a function of the time X. So let's talk variables. X is given to me as time. C of X is the monthly cost. And keeping in mind we're talking about a monthly cost is very important, because that helps me to realize that my time is measured in minutes. Minutes, how much time you're on that phone, is what will contribute to this total for the month. So C of X equals, and now let's go back and read for information, $50 per month buys 400 minutes. Now, even though this says per month, we really need to make sure we remember that we're talking about a total monthly cost. So in that month, if you use less than 400 or less, you have a flat bill of $50. If your minutes are between 0, because we can't have negative minutes, and 400. Let me say that again. In the month, we're talking about a total month here, a total monthly cost. Your bill will be $50 for that month if you keep your minutes between 0 and 400. It tells us additional time costs 30 cents per minute. So there is my M. But how am I going to get my point? We're going to get our point from taking 400 and substituting it into 50? I don't really have any work to do here. I know because this is constant, when x is 50, the output is 400. And let me not write that backwards. When x is 400, right, these are my x values. When x is 400, because ultimately we'd like to say C of 400, right? When x is 400, y is 50. So here's my m, here's my point. Let's use it. So we're going to say y minus 50 equals 0.30x minus 400 and solve. This becomes y minus 50 equals 0.3x, 0.3 times 400, minus 120. And to finish, we're going to add 50 to both sides. That gets us y equals 0.3x minus 70. This expression is what I need for the next piece. Point 0.3x or 0.30x, 0.30x, however you choose to write 0.3 minus 70. And this will be what we use to calculate your bill for the month for any minutes, any value of minutes over 400. Additional time, so past your 400 minutes, we'll use this expression. And that's it. Please let me know and remind how this went. Again, let's find our common thread with the method. So we're all good finding the first piece. To be able to correctly find the expression for the second piece, I need a point and a slope. The slope will always come directly from the scenario. The point we need to find by taking in the last x value, the biggest x value in this piece, substituting it in and getting a point. Now in this case, it's a constant piece, so there was no work to be done. But if we look at the one we had just did in number 2, we take our 50,000, and when we evaluated, we did have some math to do. That becomes the ordered pair 50,000, comma, whatever you got out, in this case 2,500. We used the m given, 8%, 0.08, and the point you just found in point slope form, and that gets us our last needed piece. Past this one, there's no more pieces. So we're done. Again, thank you very much for watching, and please let me know on Remind how this goes. See you tomorrow. Good night. Bye, guys.